Very good. So we see the title on the picture. Rob, I don't need to introduce perhaps, right?
That's fine. Yeah.
Okay, then please go ahead.
Okay. Thank you very much. So it's a pleasure and honor to be here at this conference. It's a pity that we're all doing these online now, but hopefully maybe next summer we'll all be able to meet in person. So the title there, Quantum Extremal Islands Made Easy. I'm going to be talking a little bit about ideas related to the information paradox that have been coming up recently. In fact, I like that title so much that I used it on all three of these papers here. And I have to acknowledge that I had some very talented collaborators in writing those papers. Let's see. Oh dear. Okay, here we go. So what I'm going to be talking about is in the forum of ADS-CFT, and one of the remarkable things that I've actually spent a lot of time studying there is the idea of holographic entanglement entropy. So that goes way back now to 2006 when Ryu and Takayana showed us this remarkable thing where a very difficult problem of evaluating entanglement entropy in the boundary conformal field theory could be translated to a geometric problem studying surfaces in the bulk of the ADS space-time. And there, what we're doing is we're evaluating the Bekenstein-Hawking formula on these surfaces, finding an extremal or a minimal value for those surfaces. And it turns out then that that minimal value corresponds to the entanglement entropy in the boundary theory of the degrees of freedom, say in this region A. It measures their entanglement with the degrees of freedom outside of that region. At the bottom here, I say that this became a fruitful forum for a bulk boundary dialogue. By that, I mean that well, the information flowed both ways. Of course, ADS-CFT is a dictionary between a boundary theory or a quantum field theory and quantum gravity in the bulk. But in fact, we learn new lessons about both sides of that story. We learn new things about quantum field theories. We learned new things about quantum gravity. And today, what I want to talk about is how we're learning new things about the information paradox. So I should review that a little bit. So here we have a Penrose diagram for an evaporating black hole. And so what Stephen Hawking did is he started us thinking about quantum mechanics in this context, or well, and so we can think that on an early time slice down here, the matter degrees of freedom or the quantum fields are in a pure quantum mechanical state. They can still be arranged in a way that, you know, there's excitations rushing to the center of the space, and that drives the gravitational collapse. But then he also showed that when we take into account quantum mechanical fluctuations near the horizon, that gives rise to a certain leakage of energy or quanta away from the black hole. And so radiation starts to appear out here. And that radiation is carrying away energy, and so it's making the black hole smaller. And eventually, in fact, it carries away all of the energy, and so the black hole disappears. And on this late time slice, all I have then is a cloud of radiation, diffuse radiation that's well, wandering out to infinity. Now, the problematic thing about Hawking's calculation was that he found, at least to a very high degree of accuracy, that this radiation on the late time slice was in fact thermal. And so in quantum mechanical terms, we would describe that as a mixed state. But that then was at odds with a basic tenet of quantum mechanics, namely unitary time evolution. And so if we had started with a pure state, then we should have ended with a pure state, or alternatively, if we had a pure state at the end, it should have, or if we had a mixed state at the end here, it should have started as a mixed state in the beginning. And so there's some issue here because it seems we're going from a pure state, and that's this gravitational collapse and evaporation is driving us to a mixed state. Now, I wanted to talk about entropy, and so it was really Don Page who really posed this contradiction in terms of an entropy, and what he talked about was the entropy of the radiation here. Initially, there's zero entropy because there is no radiation, but then as the black hole evaporates, that entropy just grows and grows and grows until at this late stage, the black hole disappears, no more radiation is coming out, and so the entropy is saturated here. But what Don argued, or he presented the case for, was that if this is to be a unitary process, that can't be the way things behave, of course, because we're going from, well, zero entropy for the pure state to some finite entropy for the final mixed state. And what he argued is, well, that radiation in a quantum mechanical system should be entangled with something else, namely it should be entangled with the black hole, and that the reflection of the, or the entropy of the radiation is then a reflection of that entanglement. However, in this process, the black hole is getting smaller, its horizon area is shrinking, hence its entropy, according to the Bekenstein-Hawking formula, is shrinking. And that provides a bound on how much entropy the radiation can have. And so in the case of a unitary scenario, that bound should cap off or limit how far the entropy of the radiation can go. And eventually it has to turn over and then start going down as the as the black hole shrinks down towards zero size, and in fact, it should hit zero again when the black hole has disappeared. And that turnaround time, or the Page time, is somewhere around the halfway point in the entire process. Now, he didn't present an argument that this is the way that the physics works. He simply argued that if this is to be a unitary process, this is the logical way in which that entropy should evolve. Now, the surprising thing in the past few years is that for simple, or at least a certain class of models, what we can do now is we can actually calculate that Page curve in a controlled manner. And that was really kicked off by these first two papers about 2 years ago now. But I've also included this third paper that followed up, and a lot of what I talk about is motivated by the discussion that was presented there. Of course, since then, there have been dozens of papers on this topic, investigating various aspects of it. And so this is only a partial list of the people who have continued to contribute to this progress. But I'm really going to focus on this last paper here, or I'm going to summarize their result. And the way they captured the story was with something they called the island rule. And so we should keep in mind that they changed the rule, or in these papers, we're changing the rules a little bit, in that we're coupling the black hole, or a region where there's gravity, to an auxiliary system, an auxiliary reservoir where there is no gravity, and that's what we usually call the bath. And the idea is that the black hole is emitting Hawking radiation. We're going to suck it out of that and stick it in a box or stick it in this reservoir. And there is no gravity, and we can manipulate it in the usual way that we do in quantum field theory alone. But their island rule was that the entropy of the Hawking radiation should be given by this expression here, where I'm evaluating the entanglement entropy of the quanta, or the quantum fields, in the bath region. So that's where our radiation is. But we're actually combining that region with various space-like regions in the gravity region. And these are the so-called islands. And if there's an island in this formula, we should also include a Bekenstein-Hawking contribution for the boundary of that island, much like the Rutaki. Can I just finish my sentence? I was just going to say, much like the Rutaki-Nagi formula, what we're doing is we're extremizing that expression. We're sampling all the different possibilities for the islands. If there's more than one extremum, we choose the minimum one, and that's the minimum on the end there. Sorry, was there a question?
Yes, thank you. If there is a bus, then evolution of the system is non-unitary. So
Oh, I'm not just evaluating. I'm thinking of the black hole and the bath as the total system, and it's a closed system. I'm not just considering the evolution of the gravity and throwing the radiation away. I'm including the bath as part of my system.
Okay.
Okay. So just schematically, how is that going to work? Well, at the early stages of the evaporation process, in fact, what one finds is that I can test lots of possibilities for islands, but the empty set is the extremum of this, i.e. there is no island to be included, and we're just calculating the standard entanglement entropy of the radiation degrees of freedom, and this is really Hawking's calculation, and so what we see is the entropy increasing at these early times. However, at late times, we're starting to develop a large amount of entanglement between these radiation degrees of freedom and the degrees of freedom that are in the gravity region, or in fact, in the black hole. And so this formula develops a new saddle where there now is a non-trivial island region. And so what one finds is that this part of the curve is described by this new saddle for this formula. Now, you know, there were a number of interesting ingredients for these early calculations. As I said, we were using ADS-CFT, but we had to change the rules a little bit to get these new insights. Turns out that, you know, I said that I wanted to take stuff out of the gravitating region and put it in this bath or in this reservoir. And that involved changing the usual boundary conditions that we use in ADS-CFT. It's also true that most of the early calculations focused on very simple two-dimensional models. In particular, they focused on something known as Jaquet-Teitelbaum gravity. And they also involved this idea of quantum extremal surfaces. Basically, the idea here, as I said, this is very reminiscent of the Ryu-Takayanagi formula, but it's not just that there's a geometric factor here or a Bekenstein-Hawking formula, but there are also quantum field theory contributions. And so it's the combination of quantum and geometric that goes into this idea of quantum extremal surfaces. This was already an idea that was introduced early on, but usually it was in discussions of quantum corrections or large N corrections to the Ryu-Takayanagi formula. So I want to make this a little more explicit by thinking about an example, but my example is not going to be an evaporating black hole. Rather, I'm going to do something that's computationally simpler, and I'm going to think about a black hole in equilibrium with the bath. And so again, here are our friends in Princeton who originally did this calculation. They were again looking at this JT gravity model, but it's also true that there were, I want to have matter fields running around here. And so there's a CFT that runs around in this gravity region, but also in these bath regions, which are represented by the purple. This is a bad cartoon of a diagram, but the idea is that I'm using a Euclidean path integral to prepare a very particular state here that gives the black hole and the bath in thermal equilibrium. So first of all, in the gravity region, what this semicircle is supposed to represent is the usual, Euclidean instanton that we use to describe black holes. And what we're preparing there is really the Hartle-Hawking state for the eternal black hole. This purple band is the usual flat space path integral that we do for quantum field theories. And what we're preparing there is really a thermofield double state. The fact that the geometries match up all very nicely is to emphasize that what I have is a thermal equilibrium. And so we don't really have to worry about that preparation. What we want to what I want to emphasize is that at time t equals 0 here on this dotted line, that Cauchy surface, I have radiation running around everywhere in the picture, but it's all in thermal equilibrium. There's Hawking radiation coming out, but there's also radiation falling in from the black hole. But at a macroscopic level, nothing is changing. Now, if nothing is changing, one might ask, you know, I'm in thermal equilibrium, where is the information paradox? But of course, it comes from what I was talking about before, which is at a microscopic level, the gravity region or the black hole and the purple regions, the bath, are continuously exchanging quanta. And so, for example, I might think about two quanta that are initially in the thermofield double state or in the bath. These two quanta can be correlated. This one just wanders off towards infinity. It's always in the bath, just wandering along. This one headed over towards the gravitating region. It fell into that region and in fact, eventually falls into the black hole. Now, a process like that is going to increase the entanglement, of course, between the green and the purple regions, or between the black hole region and the bath on either side of the black hole. Similarly, you can have processes where the quanta start in the gravitating region. This quanta again falls into the black hole. This one climbs out of the gravitating region and wanders off into the bath. And so what would Page's entropy curve look like there? Well, naively, this process just continues forever. And so the entropy of the radiation, or the entropy of the radiation in the bath, the change in the entropy of the bath radiation, is just increasing as more and more of these exchanges take place. However, if the black hole is really a quantum mechanical system, it can only store a finite amount of information. You can think of it as a register with a finite number of entropies, and what you're doing is you're swapping quanta between the register and the bath. Eventually, you swap all of the quanta out and replace them with bath quanta. If you continue the process, you're making new swaps of bath radiation with quanta that were originally in the bath. And so there are these extra hidden correlations between the radiation that's coming out at early times and coming out at late times. And as a result, the entropy saturates. And that's a nice story, but in fact, that's exactly what our friends found. Applying their island rule and doing some explicit calculations, they found that there was a growth phase here at early times where it was just involved calculating the usual entanglement entropy of these regions in the bath out here. But at late times, what we found, or what they found, was that there was an island region, or there was this region near the black hole that also contributed to the entanglement entropy, and in fact ensured that the entropy was saturated for the subsequent time evolution. Of course, this raises a lot of questions. How important was 2 dimensions? Was it important that we were using this particular JT, or Jaquet-Teitelboim gravity? There were questions about ensemble averages for the experts. And I'm just going to say that what I want to do today is I want to take that example, and I'm going to rephrase it, though, in a slightly different context, where I can think about gravity in higher dimensions. I can think about Einstein gravity. And in fact, I'm going to, though, do it in a way that I'm placing it firmly in the forum of ADS-CFT. And many of these new insights can be understood from familiar properties of holographic entanglement entropy. However, I've been going for a while here. There really haven't been any questions. I'm going to stop and ask if anybody has any questions. That was a lot of words. It came by very quickly, but there might be questions at this point.
Excuse me, can I ask again?
Sure, go ahead.
It was given a new definition of entropy. Let me suggest the following definition. Just minimum from 2 entropies. Entropy
Right.
of the hole and entropy of radiation. Then
Right.
the problem is solved.
Absolutely, and so I'll comment at that at the last couple of transparencies. This seems like I'm changing the rules of the game. In particular, there's a calculation of entropy involving this bath region or the bath degrees of freedom here, and then there's another formula that also is talking about the entropy of those degrees of freedom. And so, how can, well, what's going on? This seems like a very strange formula. But if you indulge me, I'll tell you a story and then I'll come back to that question towards the end of my slides. So if there are no more questions, I'll just proceed.
Oh,
Sorry, go ahead.
Can I ask?
maybe
Sure.
such a question. How do you define the boundaries between the islands and the rest, the bus region? Roughly speaking, is it correct that altogether the island plus the bath, they actually occupy the whole space-like surface? Or they are connected?
So what I'm asking is, we had this exchange going on. There was Hawking radiation leaking into the bath. And so I chose a big region here that covered most of the bath. There's a small gap between the boundary and where I'm calculating the entanglement entropy in the blue regions here. But when the island forms, it's not the entire, it doesn't form a Cauchy surface. If you like, the regions that are involved are again the same bath regions here, but there's also this isolated island or space-like region in the vicinity of the black hole. But you can see that this would be a Cauchy slice, but these red things are not part of the entanglement entropy calculation.
But how do you define these points A and B?
B is something I chose. That's the region that I chose by hand. The A was formulated by evaluating this formula and just testing out various possibilities. And what you find is you precisely define where the A is by this extremization condition.
I see. Mm-hmm.
Please, can I ask the question?
Sure.
Yes, please, Boris Altshuler. Perhaps it has nothing to do with your talk, but I see the black hole in reservoir of some another field, say of radiation. Then what's your view if they may expect some special instabilities if the black hole is in higher dimensions? Instability, this radiation in absorption by black hole and something in analogy with Ehrenfest instability of Kepler orbits in high dimensions.
Okay, if I understand what you're saying, is you're asking about, well, I'm accumulating a lot of or you might worry that I'm accumulating a lot of excitations or radiation in the vicinity of the black hole, and that might back react on the geometry and cause.
Yes, my question about possible instabilities.
Right, but well, I'll just say that back reaction, that kind of process really isn't important. It is, yeah, it won't be important in the calculations that I show you today. Maybe we can talk about it more towards the end if it's still a question.
Okay.
Okay.
Okay, thank you.
Okay, so I wanted to, oh, sorry, go ahead.
Yeah, sorry. In this scenario where you have where the black hole emits radiation and then eats some other radiation from the bath, where you talked about the swap thing going on.
Yeah.
You said that in the usual, in Hawking's paradigm, you would expect the entropy to keep increasing all the way.
Yeah.
So I just have a question here. So what comes from the bath? Is it the Hawking radiation itself coming back?
I would have said it's the other way around. The way I've set it up, the bath has a huge capacity, a huge number of quanta. And so the bath is throwing stuff into the black hole. And there's a certain sense in which after a certain point, what it's doing is the black hole's recycling those quanta and spitting them back out to the bath.
I see. So because if what's the bath giving to the black hole is the Hawking radiation itself, then it's trivial that the curve will be constant, even in Hawking's paradigm, because you know you have a two-mode squeezed state, and the one outside is entangled with the one inside. So if you throw it back inside, then you decrease the entanglement entropy of the black hole.
I'm not disagreeing with that. I'd flip the signs some places, but I'm not disagreeing with that at all.
Okay.
But let's just proceed and see where I'd like to take this. One of the things I wanted to do is I wanted to go to higher dimensions. It turns out that I want to use a tool from about 20 years ago. I want to use something called Randall-Sundrum gravity. And it's a remarkable insight, but it's a very simple system. We take our usual gravity theory that we might in ADS CFT. We have Einstein gravity here. We have a negative cosmological constant. And all we do is we stick a brane into the system. But what we do is we allow for a finite tension that then backreacts on the geometry. And I'll talk about that more precisely. But the remarkable insight of these two was that, in fact, in the backreacted geometry, we have a new graviton mode that's localized near the brane. And so that effectively you can describe the physics, at least at low energies, as a gravity theory on the brane itself. And if one, goes through some calculations, what you find is that the induced action of that gravity theory takes the following form. There's an effective Newton's constant here, and you can see that it involves the Newton's constant in the bulk, the ADS scale in the bulk. There's a cosmological constant in the brane gravity that's given by some expression like this. Here we start to see the back reaction. We have G bulk, we have the tension of the brane. Usually what Randall and Sundrum did is they tuned, in fact, this parameter to be 0. But what I'm going to do is I'm going to tune it so that it's small. I have a small negative cosmological constant on the brane. And one of the things that does for me is that, well, the next term in the expansion is an Einstein term, but then there are lots of higher derivative terms. The details don't really matter. But with this tuning, all of these contributions are suppressed by the ratio of the ADS scale in the bulk to the ADS scale on the brane. And so that's what this tuning buys for us. It gives us something that essentially looks like Einstein gravity on the brane. Now, what is this geometry? Well, we can do a trick, a cut and paste, if you like. Or alternatively, we're using the Israel junction conditions. So this disk here is supposed to be a time slice of my anti-de Sitter space. I'm actually going to foliate it with slices that are themselves ADS, but in one dimension lower. Here I've got D plus 1, here I've got a D. And so there's this extra parameter. What I'm going to then do is I'm going to choose some large value of rho, and I'm going to cut the geometry off there at some rho. Then what one does is you make a second copy of that geometry, that trim geometry, and you paste them together. And the Israel junction conditions then just relate the jump in the extrinsic curvature of that surface to the tension of the brane. And so the geometry that we're looking at then is basically anti-de Sitter space everywhere, or locally it looks like anti-de Sitter space everywhere in the turquoise region, but there's a jump in the geometry right along the green line where we glued it together. Another comment is that I could have also decided that position by just evaluating the equations of motion of our brane gravity theory, and you in fact end up with the same result. But that's just an indication, or it's because of the consistency of these two pictures, the one of D plus one dimensional gravity or the Randall-Sundrum gravity in one dimension lower, just focused on the brane. So what we have then, if I go back to ADS-CFT and the story we had there, we have now, in fact, 3 different pictures of the same system. You know, the top and the bottom, that's the usual ADS-CFT description of the system. You know, down here at the bottom, this cartoon is a picture that's supposed to convey that I have my anti-de Sitter space and I have this brane sitting in the middle of it. You know, there's this warning that this cartoon really doesn't do justice to what we have here, but it's the kind of cartoon that I'll be drawing in the rest of the talk. Now, ADS-CFT says that there's a boundary perspective where I have a conformal field theory that lives on the boundary of the ADS. The fact that I have a brane here introduces something new in the boundary perspective, and what we have is actually something called a conformal defect, or we have another conformal field theory that's just localized at that point or that intersection where the brane reaches infinity. However, the remarkable thing is that we can use Randall-Sundrum gravity to have this third description. If you like, what I'm doing is I'm only doing the holography to the conformal field theory on the defect, and I'm describing it with a gravity in this ADS, well, in this subslice or this slice, which itself is an ADS region. It's also true that in that gravity theory, there are matter degrees of freedom that are running around that are a copy, if you like, of the boundary CFT. However, one of the things we should keep in mind is that this is really only an effective theory. One of the things that Randall and Sundrum warned us is that that description comes with a cutoff, i.e. it's valid for low energies, for long wavelength excitations in the gravity region, but it's not really a UV complete, if you like, description of the theory. But I'm going to focus a lot of the discussion on this brane, what I call the brane perspective, because what we have then is a green region where we have gravity coupled to some matter fields, but that in turn couples to the rest of the boundary where I have my holographic CFT, but that's not got any gravity in that region, and so that'll play the role of the bath. I want to talk about black holes in equilibrium, and so to do that, I'm going to first go back and I'm just going to think about my ADS space. I'm going to throw away the brane for a moment, and I'm going to remind you that even empty ADS you can write in a coordinate system where it looks like a black hole. So this is a metric on empty ADS space. You can see that the way it's set up, there's a horizon at this position, rho equals L. This spatial part of the geometry actually is the hyperbolic plane, or a geometry with negative curvature. And so this is empty ADS. It actually is more like a Rindler coordinate system. And so sometimes this particular situation or these coordinates are called ADS Rindler coordinates. Now, what is this describing in terms of the boundary theory? Well, it's actually describing a thermofield double state, as usual for a black hole in ADS. But in this particular case, the thermofield double lives on this hyperbolic geometry, or 2 copies of this hyperbolic geometry across time. And there's a very particular temperature that we've chosen, where the temperature is 1 over 2 pi r, where that is the curvature scale of this hyperbolic geometry. And these geometries are just these purple squares here that lie on the boundary of my my ADS space, but I've unwrapped one of them here. And what you get is a diamond. So that looks very much like the diamond that you would think of for the Penrose diagram of Minkowski space. However, you should keep in mind that the points here, well, are representing this geometry, not flat space. Now I wanted to have this brane physics. So what do? I just take that geometry and I stick a brane in the middle of it. And so all I've done is I've added some extra degrees of freedom. And so in fact, I've really still got this thermophile double state in the boundary, but now it's the CFT coupled to my conformal defect with the same temperature here. So in this picture, the conformal defect is just a line that runs down the middle of my diamond or my space. If I look at the brane, in fact, it inherits this same kind of geometry here, but of course, some of the parameters change. In particular, the curvature scale is no longer the bulk curvature scale, but the curvature scale of the brane theory.
Rob, sorry.
Sure.
I think you have to start to converge somehow within 5-6 minutes.
Okay, I'll try and do that.
Okay.
So now we've got a system. It looks very much, well, it looks perhaps confusing, but what do I have? Again, I said that the brane perspective was the important one. I've got a picture that looks very much like the pictures I had before. I've got a gravity region. In that region, I've got something that looks like a black hole, perhaps a topological black hole. That was very much like JT gravity. I've got a bath region or these non-gravitating regions coupled to that either side of the black hole. The geometry there is a little bit different, but it's more or less the same kind of system, a gravitating region, 2 bath regions on either side of my black hole. And one of the key aspects is now we're talking about higher dimensions. We're talking about something that looks like Einstein gravity. I'm just going to remind you of something from holographic entanglement entropy. Often we find if we have 2 regions, say in the boundary that we want to calculate the entanglement entropy for, there are competing saddles or there are competing surfaces that want to tell me what the entropy is. Here I've got these 2 blue regions. Here's what I call the disconnected phase, where one of the surfaces just caps off and closes near either one of those regions. But there's a competing saddle where the extremal surface actually stretches across the ADS and joins those 2, or well, the endpoints of those 2 regions. In this phase, the sort of 2 caps are the minimal area surface, and so that's why I've shaded them in. In the you know, for larger regions, it may be that these connected surfaces are what provide the dominant saddle point and give the entanglement entropy. There's some comments about entanglement wedge reconstruction. That won't be important. So all I'm going to do, though, is take those 2 pictures and I'm going to draw some lines on them. And these are now cartoons for me sticking a brane in the space, but I'm also in this coordinate system where there's a dashed line across the middle. That turns out to be the horizon of my black hole. And what we find, if you look at this in all detail, is that at early times, this disconnected phase dominates. And here the RT surfaces or the Rutaki-Negi surfaces stretch across the horizon. As time evolves, they stretch out and the entanglement entropy grows. And so this describes the growth phase. At late times, this other phase kicks in. We're now in the connected phase. In fact, the surfaces stretch across the brane. They stay on either side of the horizon. And in fact, the entanglement entropy is fixed. And so this is the page phase where the entropy is saturated. And in fact, the entanglement wedge includes this region on the brane. And so the story from the brane perspective is very much like what we had before, and we end up reproducing the island formula. At early times, it's more or less we're evaluating the entanglement entropy in the usual way of these regions in the bath. where we're collecting the radiation. The entropy is growing, but at late times we get this new island that appears in the gravitating region. And that's really defined from our bulk perspective by the places where the RT surface went in and hit the brane. But here are some graphs. You can do it in any number of dimensions now. And I seem to have lost the dimensions, but it's 3, 4, and 5. And you're seeing the same kind of behavior in all of these different theories. You know, there were lots of questions you could ask. They're very simple answers, but the interesting question that I want to talk about is, you know, what's going on with this formula? That was, you know, a question back at the beginning. And, you know, our friends in Princeton really made a point of distinguishing the two sides of the equation. One side they're calling the full quantum description, the other side they're calling the semi-classical description. And we can see that in our discussion. Remember, I showed this slide. This is telling us just all the different ways in which we can describe the physics of this system. You know, this is where we really did the calculation with Ryu-Takanagi surfaces. But this is where, you know, what does Ryu-Takanagi tell us? It tells us what the entanglement entropy is of some region in the boundary theory. And that's really the left-hand side of that island formula. When we wanted this understanding in terms of gravity and black holes, we went to this brane perspective, and it's there where the interpretation of the island formula really appears. But again, I want to emphasize that this was an effective theory of gravity on the brane. This was really the standard or if you like, UV complete description of the system in terms of a boundary theory. So one of the things I want to emphasize is that the island rule is really just a mnemonic for the effective gravity theory. And in this framework, we're never really going to see the hidden correlations that I talked about, you know, between early and late time radiation. But it's telling us that using the variables of our effective gravity theory, we can reproduce the answer here, but it's not in doing the standard calculation that we expected, but it's doing a slightly more complicated expression given by the, by the island formula. And in any event, then I should wrap up. I just tried to illustrate some of the features of quantum extremal islands with this holographic model, where we can understand it in the form of holographic entanglement entropy, which is one that's more familiar to me at least. Have we solved the information paradox? No, not yet. And I'll just say there's lots more to explore on that. But thank you for your attention, and I guess we can have more questions.
Thank you for your talk, and couple of questions, because time is over, therefore only questions about talk, please. So,
oh dear,
raising the hands there.
Yes, can I ask?
Go ahead.
Yes,
Sure.
yes, go ahead.
Thank you very much. So I have a question actually about, more general question about the assumption behind the computation, the Euler computation, the derivation of the Ryu-Takanagi formula. If I understood correctly, yeah, if I understood correctly, basically, it seems to me that everything works if an holographic duality is assumed. Okay, so my question is, for instance, if one wants to apply all this computation of the page curve to a real astrophysical black hole, let's say just, for instance, study black hole in 4-dimensional like spatial with the non-conformal matter fields, okay, just like would this apply or not? Because it seems to me that it wouldn't.
So what I gave you is an example of a system where I understand that there are these different perspectives of the physics. You know, in particular, I understand to a certain extent, at least, you know, what this UV or quantum gravity set of variables is. If all we're given is this brane perspective, if all we're given is an effective theory of gravity, you know, Einstein gravity coupled to the standard model, you know, there's a limited amount that I can do. What this example and many other examples suggest is that, you know, I apply a formula like this, which is saying that, well, with this set of variables, I should do this calculation to evaluate the, you know, what I'm interested in. But that's really in terms of another theory that I don't know about necessarily in the standard model. That's one example, but in fact, you know, our next speaker is going to tell us other approaches or other ways to think of this that really motivate this formula more extensive, by doing more extensive calculations just with this set of variables, just working with the effective gravitational degrees of freedom. But you're right, at some level, what we're implicitly understanding or assuming is that there's another perspective, there's another duality frame of quantum gravity where everything, well, where we're evaluating things on this side of the equation.
So would you agree that, like,
okay, stop at this point.
Okay.
Time is over. Yeah.
You can send me an email
if
afterwards.
you have a short question, go ahead. If it will be speech, then we have to go to the next talk.
You're on mute, Andre.
Andre, you are mute.
Okay. Now I believe you hear me. So,
yes.
Short question, maybe more general nature. I had some more special questions, but I would just set aside. The recent progress in understanding, well, the page curve and all this stuff, does it really rule out the notion of firewall that was very popular at a certain point? What's your opinion?
I don't think we're at that stage yet. I think we've learned or we firewalls. Well, just to keep it short, I don't think we've ruled out firewalls that are, no, I think we've ruled out firewalls for standard, or it's very suggestive that there are no firewalls for standard, the black hole evaporation problem, or that they don't form there. That's not to say that I can't envision situations where there are firewalls or where there are other things happening at the horizon. But perhaps that's mysterious, and perhaps we should continue with an email conversation afterwards.
Okay. Thank you very much.